Welcome to this coding problem walkthrough. Today, we'll cover problem number 188, best time to buy and sell stock for. This is a challenging yet highly practical problem that focuses on maximizing profits from stock transactions with a constraint on the number of allowed trades. By the end, you'll have a clear understanding of the problem and a structured approach to solving it. Let's dive in. In this problem, you're tasked with designing an algorithm to maximize your profit from stock trading. You're given an integer k, representing the maximum number of transactions you can make, and an array called prices, where each element prices, I, represents the stock price on the ith day. The challenge is to figure out the maximum profit you can achieve by completing at most k transactions. Now, keep in mind a crucial rule: you cannot engage in multiple transactions at the same time. This means you must sell a stock before you can buy another one. The input consists of two parts: k, the maximum number of transactions, and prices, an array of stock prices. The output is a single integer, which represents the maximum profit achievable under these constraints. For example, let's consider the first case. If k is 2 and the prices array is 2, 4, 1, the output would be 2. Here's why: you could buy the stock on day 1 when the price is 2 and sell it on day 2 when the price is 4. This gives you a profit of 4 minus 2, which is 2. Since you're allowed at most 2 transactions, and there's no further profitable transaction possible, the total profit in this case is simply 2. Now, let's look at another example. If k is 2 and the prices array is 3, 2, 6, 5, 0, 3, the output is 7. This is because you can make 2 profitable transactions here. In the second example, you can first buy the stock on day 2, when the price is 2, and sell it on day 3, when the price is 6. This results in a profit of 6 minus 2, which is 4. Then, you can make a second transaction by buying the stock on day 5, when the price is 0, and selling it on day 6, when the price is 3. This gives another profit of 3 minus 0, which is 3. Adding these together, the total profit is 4 plus 3, which equals 7. Now, consider the constraints: k can range from 0 to 100, the prices array can have up to 100,000 elements, and stock prices can go up to 10,000. Some edge cases to keep in mind include when the prices array is empty or when k is 0, as in both cases the profit would be 0. If k is very large, such as greater than half the length of the prices array, the problem simplifies to the case of unlimited transactions. Finally, if the prices are in descending order, no profit can be made, and the maximum profit would also be 0. To solve this problem, we start by exploring 2 main approaches. The first is the brute force method. Here, the intuition is simple: simulate every possible combination of buy and sell transactions, up to k transactions in total. For each combination, calculate the profit and track the maximum. However, this approach is computationally expensive because it involves examining all possible subsets of buy and sell days, leading to an exponential time complexity of O(2 to the power of n). As a result, this method quickly becomes unfeasible for even moderate input sizes due to its inability to scale efficiently. On the other hand, we have a more structured and efficient approach using dynamic programming with state variables. This builds on the intuition developed in the buy and sell stock series, but generalizes it to allow up to k transactions. The key idea here is to define states that represent the maximum profit at each day while managing up to k transactions. Specifically, we use 2 key states: hold, which tracks the maximum profit on a day when holding stock after t transactions, and cash, which tracks the maximum profit on a day without holding stock after t transactions. These states allow us to make optimal decisions based on previous transactions and ensure we maximize profit efficiently. With dynamic programming, the transitions between states are crucial. If we are holding stock on day I after t transactions, the maximum profit can be calculated as the maximum of continuing to hold the stock from the previous day, or buying stock on day I after completing t1 transactions. This is represented by the formula: hold t I equals max hold t I1 cash t1 I1 prices I. On the other hand, if we are not holding stock on day I after t transactions, the maximum profit is the greater of continuing to not hold stock from the previous day, or selling stock on day I. This is expressed as cash t I equals max cash t I1 hold t I1 plus prices I. We also define base cases. If no transactions have been made, hold 0, I equals prices, I representing the cost of buying stock, and cash 0, I equals 0, as no transactions mean no profit. This structured approach ensures that we only calculate what's necessary, leading to a time complexity of O, k asterisk n, where n is the number of days. While the space complexity is also O, k asterisk n, it can be further reduced through optimization. To address the space complexity, we apply a space-optimized version of dynamic programming. Instead of maintaining a full 2D DP table, we reduce memory usage by keeping track of only the previous state. This is possible because each state transition depends solely on the values from the previous day. To achieve this, we use two 1D arrays, prev_hold and prev_cache, to represent the states of holding and not holding stock for the previous transaction count. These arrays are updated iteratively for each transaction count t, enabling us to achieve the same results with a much lower memory footprint. This space optimization reduces the complexity to O, n, while maintaining the O, k asterisk n, time complexity. Among the approaches considered, this strategy strikes the right balance between computational efficiency and simplicity. By leveraging dynamic programming with state variables, along with space optimization, we ensure that the solution is both scalable and practical. When comparing the different approaches, we see clear trade-offs. The brute force method, while conceptually straightforward, is computationally prohibitive for real-world input sizes due to its exponential growth in complexity. The dynamic programming approach with state variables, on the other hand, is efficient and scales well with larger inputs. Adding space optimization makes it even more practical by significantly reducing memory usage. While greedy strategies are often useful for simpler stock trading problems, they are not applicable here due to the constraint of at most k transactions, which requires careful tracking of states to ensure optimal decisions. Ultimately, the chosen strategy of dynamic programming with space optimization provides the best balance of accuracy and efficiency, making it well suited for both competitive programming scenarios and real-world applications where time and memory constraints must be considered. To solve the problem of maximizing profit with at most k transactions, we use a dynamic programming approach. The main idea is to define the state dp, I, j, where dp, I, j, represents the maximum profit we can achieve on day j using at most I transactions. Here, I ranges from 0 to k, and j ranges from 0 to n1, where n is the number of days. For the base cases, we know that if no transactions are allowed, the profit is 0, so dp, 0, j, equals 0 for all j. Similarly, if we only have the first day to work with, no profit can be made, so dp, I, 0, equals 0 for all I. The transition involves making a decision for each day and transaction count. On any given day j, we can either choose not to sell, carrying forward the profit from the previous day, or sell on that day. If we sell, we need to calculate the best profit achievable by buying on a previous day, which leads us to the concept of max_diff, a rolling value that helps track the maximum difference between profits from previous transactions and the stock price on those earlier days. To elaborate on the transition formula, when we decide not to sell on day j, the profit remains dp, I, j, equals dp, I, j1. However, if we sell on day j, the profit is determined by adding the current stock price, prices, j, to the max_diff value. This max_diff represents the maximum profit achievable by buying on any prior day t, or t less than j. The transition formula is then given by dp, I, j, equals max, dp, I, j1, prices, j, plus max_diff. To compute this efficiently, we maintain and update max_diff as we iterate through the days. For every day j, max_diff is updated as max_diff, dp, I1, j1, prices, j1. This avoids recalculating the maximum difference for every day, ensuring the algorithm remains efficient. Once we compute all the values in the dp table using nested loops, where the outer loop iterates over the number of transactions and the inner loop iterates over the days, we can find the desired result stored in dp, k, n1. Which represents the maximum profit achievable using at most k transactions by the last day. Dynamic programming is an ideal approach for this problem because of its overlapping subproblems and optimal substructure. For example, the profit from I1 transactions directly impacts the calculation for I transactions, making it essential to build on previously computed results. Additionally, the use of max_diff significantly optimizes the process by reducing redundant computations. Instead of recalculating the maximum difference for every day, we maintain a rolling value that gets updated as we iterate through the days. This optimization reduces the complexity for each transaction level to O(n), making the solution efficient even for larger inputs. By iterating through the days only once for each transaction level and storing intermediate results in the DP table, we avoid the exponential complexity of a brute force approach. The DP table and max_diff rolling variable together form the backbone of this solution, allowing us to systematically break the problem into smaller, manageable subproblems while maintaining efficiency. The purpose of the DP table is to store the maximum profit achievable with I transactions up to day j. It has dimensions, k plus 1, xn, with rows representing the transaction count and columns representing the days. This structure allows us to systematically compute results for smaller subproblems and reuse them for larger ones. Meanwhile, the max_diff variable tracks the maximum value of DP, I1, T prices, T, for all prior days T up to the current day J1. This rolling variable eliminates the need for recomputation in the inner loop, significantly improving efficiency. In terms of complexity, the algorithm runs with a time complexity of O, k*n, because of the nested loops, one for transactions and one for days. Space complexity is also O, k*n, due to the size of the DP table. However, we can optimize space by storing only the current and previous rows of the DP table, reducing space complexity to O(n). Handling edge cases is also crucial. If k is 0 or there's only one day of price data, profit is 0. Additionally, when k exceeds n/2, the problem reduces to the unlimited transactions case, as more than n/2 transactions would be redundant. Finally, let's review the edge cases and pseudocode for clarity. If the prices are strictly decreasing, no profit can be made, as every buy-sell pair results in a loss. For the pseudocode, the first step checks if the input is trivial, such as when k or the number of days, n, is 0. In such cases, the function immediately returns 0. If k is very large, the problem simplifies to the unlimited transactions case, which we solve by summing the profits from all upward price movements. For the general case, we initialize the DP table with zeros and iterate through transactions and days. Within the nested loops, we maintain and update max_diff while calculating the profit for each day using the transition formula. At the end of all iterations, the maximum profit with at most k transactions is stored in DP, k, n1. This structured approach ensures that the algorithm is both efficient and easy to understand, making it suitable for real-world applications where input sizes can be large. This code solves LeetCode problem number 188. Best time to buy and sell stock for using a dynamic programming approach. The goal is to maximize profit using at most k transactions over the given stock prices array. First, the code handles edge cases where the prices array is empty, n equals 0, or the number of transactions k is 0, immediately returning 0 since no profit can be made. Next, it checks if k is greater than or equal to half the number of days, n/2. If true, this means we can perform an unlimited number of transactions. In this scenario, it calculates the maximum profit by summing up all positive price differences, prices I1, for prices I1. This greedy approach is optimal for unlimited transactions. For the general case where k is limited, the code uses a dynamic programming table DP. Here, DP, I, j, represents the maximum profit achievable on day j with at most I transactions. The table is initialized with dimensions, k plus 1, xn, filled with zeros. The outer loop iterates over the number of transactions I from 1 to k. For each transaction level, it maintains a max_diff variable, which stores the maximum difference between the profit from the previous transaction, DP, I1, j, and the price on day j. This helps in efficiently calculating the profit for the current transaction. The inner loop iterates over the days j from 1 to n1. For each day, the code calculates the maximum profit by either 1. Not selling on day j, taking the previous day's profit DP, I, j1, or 2. Selling on day j, which adds the current prices, j, to max_diff. After updating dp, I, j, the max_diff is also updated to reflect the best difference seen so far, dp, I1, j, prices, j. Finally, the maximum profit for k transactions is stored in dp, k, n1, and returned as the result. This approach ensures optimal performance with a time complexity of O, k*n. Here, we begin the Java implementation for solving the problem. First, we import the necessary utilities and define our class and method. The method takes two inputs, an integer k representing the maximum number of transactions allowed, and an array prices representing the stock prices on different days. We start by getting the length of the prices array, and if either the array is empty or k is 0, we return 0 immediately, as no profit can be made. Next, we handle an edge case where k is greater than or equal to half the number of days, which essentially means we can make unlimited transactions. In this case, we iterate through the price array and add up all positive price differences between consecutive days to calculate the maximum profit, which is then returned. If this condition isn't met, we proceed to initialize a 2D dp array where dp, I, j, represents the maximum profit achievable with I transactions up to day j. We then enter a nested loop to fill this dp array. For each transaction count I, we start by calculating max_diff, which helps us track the optimal point to buy stock for this transaction cycle. Inside the inner loop, we calculate the maximum profit up to the current day by either not selling today or selling today and using max_diff for the best previous buy point. As we continue with the inner loop, we update max_diff by taking the maximum of its current value and the profit from the previous transaction count minus the price of the stock on the current day. This ensures we are always tracking the best opportunity to buy stock for maximizing profit in the current transaction cycle. Once both loops complete, the dp array will be fully populated with the maximum profits for all combinations of transactions and days. Finally, we return dp, k, n1, which represents the maximum profit achievable with k transactions over all the given days. This concludes the implementation, efficiently solving the problem using dynamic programming with a time complexity of O, k*n. Here, we start with a small input where the number of transactions allowed, k, is set to 2, and the prices array is 2, 4, 1. The length of the prices array, n, is 3. Since k is less than n divided by 2, we use dynamic programming to solve the problem. We initialize a 2D dp array of size, k plus 1, by n, filled with zeros. The dp array will help us track the maximum profit at each step. For the first transaction, where I equals 1, we calculate a helper variable max_diff, which starts as negative of the first price, or -2 in this case. This max_diff helps us efficiently compute the maximum profit by keeping track of the best price difference so far. For j equals 1, we update dp, 1, 1, to the maximum of dp, 1, 0, and the current price plus max_diff. This gives us a value of 2 for dp, 1, 1. Then we update max_diff for the next step. Similarly, for j equals 2, dp, 1, 2, remains 2 since adding max_diff to the price doesn't yield a higher profit. Finally, we move to the second transaction, where I equals 2, and repeat a similar process. In the second transaction for this example, starting with I equals 2, max_diff is reset to prices, 0, which is -2. For j equals 1, we calculate dp, 2, 1, as the maximum of dp, 2, 0, and prices, 1, plus max_diff, which results in 2. Max_diff is updated to -2 as the calculation does not improve it. For j equals 2, dp, 2, 2, also remains 2, as the maximum profit with 2 transactions doesn't increase with the available prices. At the end of this step, the final dp table shows the maximum profit for each combination of transactions and days. The table is 0, 0, 0, 0, 2, 2, 0, 2, 2. The output, which is the maximum profit achievable with 2 transactions, is dp, 2, 2, or 2. Next, we'll look at an example with a larger input where the number of transactions is sufficient to treat the problem as having unlimited transactions. In this example, k is set to 3, and the prices array is 3, 2, 6, 5, 0, 3. Since k is greater than or equal to n divided by 2, where n is the length of the prices array, 6 in this case, we can treat this scenario as having unlimited transactions. In such cases, the problem simplifies to summing up all positive price differences between consecutive days. Starting with prices 1, prices 0, we see a difference of -1, which does not contribute to profit. However, prices 2, prices 1 gives 4, so we add this to the profit. Similarly, prices 3, prices 2, and prices 4, prices 3 yield -1 and -5, respectively, which do not contribute. Finally, prices 5, prices 4 adds a profit of 3. Summing up the profits from positive differences, we get a total profit of 4 plus 3, which equals 7. This is the output for this example. Now, let's consider a larger input where the number of transactions is limited, and we'll use dynamic programming to solve it. In this final example, we have k set to 2 and the prices array as 3, 2, 6, 5, 0, 3. Here, since k is less than n divided by 2, where n is 6, we use dynamic programming to solve the problem. We initialize a DP table of size, k plus 1, by n, filled with zeros. For the first transaction, where I equals 1, we start by setting max_diff to prices, 0, which is -3. For j equals 1, dp 1, 1 remains 0 since the profit calculation doesn't yield a positive value. For j equals 2, dp 1, 2 updates to 4 as adding max_diff to the current price gives the maximum profit so far. Continuing this process for j equals 3, 4, and 5, we update dp and max_diff accordingly. For the second transaction, where I equals 2, we repeat similar steps, updating dp values row by row. The final dp table is 0, 0, 0, 0, 0, 0, 0, 0, 4, 4, 4, 4, 0, 0, 4, 4, 4, 7. The maximum profit with 2 transactions, which is stored in dp 2, 5, is 7. This concludes the solution walkthrough for the problem. To analyze the time complexity of the solution, we start with the preliminary checks. These include verifying whether the number of days, n, is 0 or if the maximum transactions, k, are 0, both of which take constant time, o, 1. If the number of transactions allowed, k, is greater than or equal to half the number of days, n, the algorithm simplifies to calculating the maximum profit for unlimited transactions. This only requires a single pass through the prices array, resulting in O, n, time complexity. Now, for the dynamic programming approach, the DP table is initialized with dimensions, k plus 1, xn, which takes O, k asterisk n, time. Next, we have 2 nested loops. The outer loop iterates over the transaction count, I, from 1 to k, running O, k, times. The inner loop iterates over the days, j, from 1 to n, running O, n, times for each transaction. Inside the inner loop, each operation, whether updating the DP table or calculating the maximum difference, is constant time, O, 1. Therefore, the nested loops contribute O, k asterisk n, time. Combining all these factors, the overall time complexity is determined by the specific case being solved. Now, let's summarize the total time complexity. If the condition k equals n//2 is met, the solution computes the profit in O, n, time. Otherwise, when the dynamic programming approach is used, the complexity is O, k asterisk n. Moving on to space complexity, the DP table occupies a 2D array of size, k plus 1, xn, resulting in O, k asterisk n, space. Additionally, the variable max_diff is used during each iteration of the outer loop, but since it only requires a single value at any given time, its space complexity is O, 1. Considering these factors, the total space complexity is dominated by the DP table, which is O, k asterisk n. This balance of time and space demonstrates how the algorithm is optimized compared to more naive approaches. Looking at best, average, and worst case scenarios, the best case occurs when k equals n//2. In this scenario, the algorithm skips the DP table entirely and computes the result in O, n, time, making it highly efficient. For both the average and worst cases, when k less than n//2, the DP approach is necessary, leading to O, k asterisk n, time and space complexity. To put this into perspective, compare it with the brute force approach. A naive solution would involve generating all possible combinations of k transactions, which requires n to the power of k time because each transaction involves iterating through the prices array, and there are k-nested loops. Such an approach is computationally expensive and impractical for large inputs. On the other hand, the optimized dynamic programming approach reduces the time complexity to k*n by leveraging intermediate results, while also keeping space usage to k*n, a significant improvement in scalability. Finally, let's break this down into a mathematical proof of the big O complexity. For the dynamic programming approach, the outer loop iterates k times for each transaction level. The inner loop runs n times for each day in the price array, and every operation within these loops, such as updating the DP table or calculating max_diff, is constant time, 1. Combining these, the total time complexity becomes k*n. On the space complexity side, the DP table requires storage of size, k plus 1 xn, which results in k*n space. By systematically reducing redundant calculations and storing intermediate results, the algorithm achieves a significant optimization over brute force, making it well-suited for handling larger inputs efficiently. When tackling this problem, there are several common mistakes to watch out for. First, ignoring edge cases such as when k is 0 or when k exceeds n/2, where n is the number of prices. If k is 0, no transactions are allowed, and the answer is simply 0. On the other hand, if k is greater than n/2, the problem simplifies to the case of unlimited transactions, which can be solved with a greedy approach rather than dynamic programming. Another frequent issue is confusing the buy and sell states in dynamic programming. Properly transitioning between these states is essential to ensure that profits are calculated correctly. Additionally, relying on brute force methods for large inputs is a pitfall, as this approach becomes computationally infeasible for larger n, such as 10,000 prices or more. Failing to use dynamic programming or greedy optimizations in these cases often leads to timeout errors. Lastly, overlooking overlapping subproblems can significantly impact performance. Without memoization or tabulation, you may end up recalculating the same subproblem multiple times, which results in exponential time complexity and inefficient solutions. Another common issue involves mismanaging space complexity. For example, many solutions use k*n space for dynamic programming tables, but more space-efficient methods exist. By reusing previous computations, you can reduce this to n space. Beyond implementation, it's important to approach the problem strategically during interviews. Recognizing patterns in state management, such as whether you're holding a stock or not, can help you generalize solutions across related problems. If asked about a brute force solution, it's a good idea to explain its inefficiencies before transitioning into optimized approaches like memoization or tabulation. Always take the opportunity to clarify constraints with your interviewer, such as the value of k and the size of the input array, and proactively discuss edge cases. Finally, be prepared to discuss trade-offs, particularly between time and space complexity, as this shows a deep understanding of the problem and your solution's efficiency. This type of problem is closely related to several other stock trading problems, each varying in complexity. For example, best time to buy and sell stock I allows only one transaction, making it the simplest version of the problem. Best time to buy and sell stock 2, on the other hand, permits unlimited transactions, which can be solved using a greedy approach. Best time to buy and sell stock 3 builds on this by limiting transactions to at most 2, requiring more complex dynamic programming. Finally, the problem at hand, best time to buy and sell stock 4, generalizes these scenarios by allowing up to k transactions. Understanding these related problems can help you recognize patterns and apply similar strategies depending on the constraints. There are several approaches to solving this problem, each with its own trade-offs. A recursive approach with memoization is conceptually easier to implement and can handle overlapping subproblems, but it still uses k*n space and is slower for large inputs compared to iterative solutions. Iterative dynamic programming with tabulation is generally more efficient, with a time complexity of k*n, and its space usage can often be optimized to n. However, it requires careful management of state transitions. For cases where k is greater than n/2, a greedy approach works well, running in n time with 1 space. That said, it cannot handle scenarios with limited k constraints. Lastly, space-optimized dynamic programming is another option, reducing space complexity to O(n) by reusing computations. While efficient, it can be harder to debug and may require additional explanation during interviews. Choosing the right approach depends on the problem constraints and the trade-offs you're willing to make between simplicity, efficiency, and clarity. Great job sticking through the problem. To wrap up, we covered how dynamic programming can be applied to optimize stock trading problems, ensuring an efficient solution. Remember the state transitions and constraints we discussed, they're key to solving similar problems. Don't forget to like and subscribe for more coding tutorials. Thanks for watching, and I'll see you in the next one. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!